Hello. So in this section, we're going to look at something called factorial notation. So before we, let's look into it then. So first of all, let's consider this, right? Let's consider the multiplication, say 5 times 4 times 3 times 2 times 1. If you were to put that, say, in a calculator, you'd get 120. What if we then wanted to do, say, 6, right? 6 times 5 times 4 times 3 times 2 times 1. Wow, that's 6 times 120, right? And then we get 720. And then actually we can repeat this process for 7, 8, 9. And so hopefully you spot the idea is that we're timesing all the integers together up to that point, right? So we times all the numbers from 1 up to 5 and then 1 up to 6, okay? We can actually express that sort of multiplication in terms of something called a factorial. And we say this, n exclamation mark, meaning factorial. Okay, that's how we say it. And what this does is essentially it defines what we've just done up here. So n factorial is essentially the multiplication of the first n numbers, right? The first n integers. So it'd be n times, and then the next one down would be n minus 1. Then the next one down after that would be n minus 2. And then we repeat that and times again and again until we get to the last few integers, 3 times 2 times 1. So again then, using our examples above up here, we could say then that 5 factorial would be 120, 6 factorial would be 720, and then we can go so on as well. And it turns out the calculator has a function, has this factorial function in the calculator, so you don't have to write out all the times. So the calculator will give that factorial of a number straight away. I'll look at that in a minute because we're going to look at something else as well. Once we look at that, I'll show you how to do that. So that's the factorial, and that's factorial notation. Now, that is helpful in our work with binomials because what I'm then going to talk about is, let's remind ourselves of Pascal's triangle. So again, last time we looked at Pascal's, it was ones on the edge, right, on either side. And then as we go down the triangle, as we create more rows underneath, then it's 1 here and then 1 at the end. And then in between two numbers, we then add them and then say here, 1 and 1 gets us 2. Then we go to the next row, add 1s outside. Then 1 and 2 here gets us 3, and 2 and 1 also gets us 3. And we can go down again, 1, and then 1 and 3 gets us 4, 3 and 3 gets, and that is a 3, gets us 6. 6 and 3 and 1 gets us 4, and then a 1 outside. And so we can repeat that pattern, right? And we use that to find coefficients. For example, then, if we were to expand, say, x minus 2 cubed, well, instead of times in the bracket 3 times, what we could do is use this triangle to give us the coefficients of each term. So first of all, the power is 3, so we want row 3. However, remember we started from row 0. Alright, we called the top row 0 instead of 1, because we will include terms and powers that are 0, okay, and we'll see that in a second. So that was row 0 we start from, then we had row 1, row 2, the row underneath, and row 3. And there we are. So we want the row number that matches the power, and that will then tell us if we highlight, oh, it's a bit messy, but row 3, if I rewrite it a bit clearer, if I box it, then these are the coefficients, the numbers, the row I'm interested in. So how would I use that then in this expansion? Well, then that would be the coefficient in order of each term. So firstly, our first term in this expansion, well, it could be x cubed, right? That would be the highest power, right? X cubed. Then the coefficient then is 1, because that's the first number in the row. And then we times that by the number in the other number in the bracket, -2, and then that has to be a power of then 0, because we want the two powers 3 and 0 to give us 3. Okay, we always want the powers overall to be 3. Then we move on to the next term, which would be x squared, but then the next coefficient would be 3, so then we have 3 lots of x squared. Then -2, the other number then would then be to the power of 1, because then the x squared and 2 and 1 gets us 3. Then the next term, the coefficient would be 3. Then we would have x as we're knocking down the power then. So 3x, and then that would be x to the 1 as well. Then the -2, the other number in the bracket, would then be to the power 2. Because again, 1 and 2 gets us 3. We need to match the power of the bracket. And then eventually, we then get the last term. Well, then the coefficient would be 1. That's the last number in the row. And so then we'd have x to the 0. Okay, knock off a power again. And then -2 would be then to the power of 3. So hopefully you recognise we are going down powers of x, but also we're going up in powers of -2. And we start from powers of 0. Hence why we need to start from row 0 there. As we get powers of 0 there, right? So yeah, and so then if we were to just expand the bracket, simplify, well, firstly -2 to the 0 here would be just 1, and if it's power of 0 is 1, so we just get x cubed. Then we have for the next term 3 lots of x squared times -2, that'd be -6x squared. Then we had 3x of -2 squared. Well, -2 squared is 4. 4 times 3 is 12. So 12x. Then lastly, 1 lots of x to the 0. Well, x to the 0 would be 1. So we just get -2 cubed, which would then be -8. And that is our expansion. So yeah, the Pascal's triangle then allows us to determine the coefficients for each term if we were to expand it. And that's generally the process, right? However, okay, well, that is good, especially for slightly higher powers where we don't have to expand so many brackets. The problem is, again, we have to, if we want to find higher powers, say if we wanted a 10th power or 100th power of a bracket instead of just 3, well, we have to, again, we'd have to keep continuing going down the triangle. And the problem is, well, we have to go through so many rows to get to a higher power that we want. And so again, that's not the most efficient way. So then, what if there was a way we could just work out the coefficients that we want, right? Because we want the numbers in a row. Is there a way without having to just go down the rows of just quickly being able to get any row, any power that we want, and to get all the coefficients of a row? So any row, is there any way we can do that without having to just go down row by row by row down the triangle until we get where we want? For example, again, if we had x minus 2 to the 300th, how on earth would we be able to find the coefficients going down 300 rows or so, right? And that's where this this next idea comes from. It turns out that we have this function called, and it looks a bit like a vector, nr, and we say this is called n choose r, okay? So this is called the choose function, or we could say n big C subscript r, okay? So a small n above the C and the r down there. So there are two ways of saying n choose r. Now that is a That will also be in the calculator, which I'll show how to do in a second. But this also has another definition of NR, and again it looks like a vector but it's not. We say it's N choose R, okay? That's the language we use. N choose R, and it also, while using our factorial function, or why we introduce factorials, is we can say this is N factorial over R factorial of N minus R factorial. Okay, and that is a formula in the formula book, by the way. Yeah. Uh, and it looks really weird at first, but when we look for examples, you'll get more used to it. But that tells us, we can use the right fraction, and that's how we define this choose function. But again, the choose function will be on the calculator. But why am I bringing this up with Pascal's triangle? As I said, this NR allows us to input, if we can input a value of N and a value of R, which allows us to directly, in the calculator, to directly get a particular coefficient, right? From the triangle, without having to go down the triangle and do all the above rows first. So we can instantly obtain all the coefficients, which will allow to make expansions even quicker. And we will be using that next section. But as for now, using this function, okay, now I've said this corresponds to the terms in the triangle, right? But what exactly do I mean by that? Well, remember I discussed we start from row 0 instead of row 1 because of the fact we're dealing with powers in the expansion of 0. Remember, in this example, we had we have powers of x to the 0, and we have minus 2 to the 0. Both numbers in a bracket in an expansion, you have to include powers of 0 in the expansion. So we have to start from row 0. With that in mind, well, N choose R, essentially, N corresponds to the power number, right? The 3 here. Okay. And R corresponds to the term number, right? That you want. So, for example here, I'm going to bring this back again. X minus 2 cubed. I want the coefficients of all the terms. But instead of just reading from Pascal's triangle, I'm going to start to use this formula. So remember, because it's row 3 here, and the power is 3, I read off the terms, the numbers from this row to give me the coefficients of each term. So using this choose bracket function, this sort of weird bracket, well, firstly, again, we have n would be 3 because that's going to be the power number. That tells me the row number, right? So remember, it's row 3 here, even though obviously there's 4 rows technically, but we start from row 0. But because the power number is 3, I want row 3, so n would be 3. Then R is going to be corresponding to the number, the position of the coefficient in the row. So, again with that, we start from 0. So actually, this 1 here would actually be the 0th position in the row. So that means then 3 and then R is 0 would then be number 1. Right? Then, if we then wanted to do the next term, if we wanted to do 3, well, first it's in row 3, so n is 3 again. Then R, sort of the position number in the row. Well, that's going to be, we start from 0 again, so it's going to be the sort of position 1, right? So this one here, the 1 here, was position 0, hence 0. Now, position 3, the 3 here, it's in position 1, so it's going to be R is 1 there. And again, that then gives us 3. That coefficient there would be 3. Then this 3 here is in the second position. Obviously, we start again to iterate. We start from a 0 again, and then we go the way. Then we go up. So that'd be then the second position. So from row 3 again, and then the second position in the row. That would then get us 3 again from Pascal's triangle. Then lastly, to show that we get the 1 at the end. Oh, here. Well, again, it's in row 3, which again corresponds to the power here, 3. So that's 3, and then the sort of the position number in the row. That's the third term, right? With the third position, right? So that'd be 3, and again that'd be 1. And so this gives us a way we can sort of generalise this, and gives us an instant way without having to refer to Pascal's triangle to give us all the coefficients of each term, which we'll be using more next time. But hopefully for this section, to try to get more comfortable with it, how we can go from Pascal's triangle to then using this factorial, this choose function, this sort of n choose r bracket thing, to get comfortable with that notation, and using that instead to get instant values no matter what. And so again, we start from 0. Again, the idea is we start from 0 and then we go our way up to we start from row 0 to 3 or whatever, and then in the row itself, we start from position 0 to position 3 at the end. And the idea is the number here. So again, nr, r should never exceed n. So if we said 3, 4, that wouldn't be a thing. So there's something wrong there. So hopefully you see then that really the 3 corresponds to the power, and 0, and then we have 0, 1, 2, and 3, right, as the r. That's sort of like the term, the coefficient of the term we're interested in. So this is almost like the 0th term. The 1 here is like the 1th term. The 2 is the second term, and the 3rd is the 3rd term. What I mean by that is, it's kind of like 0. We could say it's the x to the 0th term, right? The first term is x to the 1th term, if that makes any sense. 2 corresponds to the x to the 2th term, and the 3 at the end here, r is 3, corresponds to x to the 3rd term. If that makes any sense. So it corresponds to basically the different powers of x, the coefficient of each power of x, right? Because remember, in expansion, we have all different powers of x up to the final power, which is 3. Anyway, so we'll look at some examples now with that in action. But that's the sort of idea to how we use this notation. Actually, I'll do one more example. Very simple example. Let's do x minus 1 squared, right? So using this notation, well, the power's 2. Say if you want the 0th term here, so that's going to correspond to x to the 0. So that's going to, if you read off Pascal's triangle, the 2 choose 0 is going to be from row 2, which is going to be then here, n is 2. Then r is 0, it's going to be like the 0th position. That's going to then give us 1. Then 2 choose 1 is then going to be 2 here. And lastly, 2 choose 2 is going to give us 1 there, okay? And so if we were to then expand it this way, well, again, these tell us the coefficients, right? So firstly, if we start from here, this is sort of like the x to the 0th term, so x to the 0, and then the coefficient is 1. Okay, but then we have the -1 as well. And then that would be the power of 2, because again we've got to match the powers to 2. So 0 and 2 will be 2. But the 1 here matches the coefficient there that we worked out. Then the next term, well, that's when x is what? X to the 1. Then the coefficient is 2. So then it's times by 2, times by then the number -1 to the power of 1. Because then both powers add up to 2. Then lastly, 2 here, r is 2. That corresponds to x squared, x to the 2, times by coefficient of then number 1, then times by the -1 in the bracket here, and then that be to the power of 0, because then 2 and 0 gets us 2. So then if we were to expand the brackets, well, x to the 0 is just 1. So 1 times 1 times -1 squared, that's just 1. Then x to the 1, which is x, times 2 times -1, that'd be -2x. And then lastly, x squared times 1 times -1 to the 0. -1 to the 0 is just 1, so we just get plus x squared. Okay, we will be looking at plenty of examples of expanding in this way. So if it's a bit confusing, we will look at more. But I'm just trying to... The main idea for this section is to try and start to get a head around using this bracket, this sort of choose function, this weird bracket notation. Okay, so I'm going to then explain how we can do that on the calculator. Right, so, because you don't need to use Pascal's triangle to read off the values. So let's have a look. So, firstly, the factorial function, right? The n factorial part. So that again is n times n minus 1 times ... times 2 times 1. So the multiplication of the first n numbers. We can do that on the calculator. If I can find it. Here, right? It's the x to the -1 button. But if it's in yellow, right? It's in yellow, so we have to go in shift mode. So if we get rid of that, we go in shift. Then that'll give us the exclamation mark, which means factorial. If we then go to the left and say type in 5 factorial, answer 120. Well, there we are though. We discussed that 5 factorial indeed is 120. Then we could do it for any other integer. Say instead of 5 factorial again, let's do 9 factorial. So then 9, and then we need to get our factorial or exclamation mark. That'd be then shift to put it in the yellow mode, if you will. Then the factorial button there will get me that number. Right, and so that is 362,880. So the numbers will get big very, very quickly. So it's good we have resources like the calculator that works it out for us. Okay, so that's very quickly how you use the factorial. Now the choose function, let's reset it. There we are. If we then need to use the choose function, it's here. It's this division symbol here. But obviously, again, it's this NCR. So the calculator will use this notation, which again means N choose R, which is that same as NR. That bracket N choose R. So if we put that in the calculator, then we need to go in yellow mode. And so there it. Oh no, that's P. Here and then here gets us that C. Okay. Now we're reading N choose R, so we need our N number first. So let's say that's N is 3, and then R is say 1. So then 3 choose 1 would then get us 3. Well, hang on, isn't that what we got over here? Yeah, 3 choose 1 is 3 here. Then if we did 3 choose 3, that indeed gets us 1 as well, which is here. So there we are. So it kind of matches what we expect. And we can do it for absolutely any sort of any choice of n and r. So say if we then said n was 100, and then we had the 50th term, that tells us the coefficient then would be that. So that is a huge number, but the calculator instantly gives us it, right? Without having to go through like 100 rows down the Pascal's triangle, and it'd be an absolute nightmare because this is a huge number, right? 10 to the 29, all massive. But our calculator does have the facility to calculate that. Okay, then say if we let's maybe say if we had 6, choose 4, say. So 6 and then choose, we need the C, so shift and then over here. And then we had 4, that gives us 15, so that's telling you the coefficient part of the 4th term, so x to the 4 of a power of bracket of 6. So it would be 15, okay? So for example, if we had x plus 1 to the power of 6, the x to the 4th term would be the coefficient part tells us it's 15, right? Times then x to the 4, right? Then 1, which is the other number, 1 to the 2, right? Because then 4 and 2 gets us 6. But then overall, if we work that out, that's just 15x to the 4, right? I should probably actually, that'd be 15x to the 4, right? So there we are. So we can very quickly, we even with the calculator, we're using this choose function, allows us to instantly get any coefficient of an expansion. So we don't need to rely on Pascal's triangle, although these values do come from Pascal's triangle. It's just that we don't need to do it by hand, right? The calculator has the technology to do it for us. But there is an alternative way as well with this as well. In terms of factorials, that's the definition for it. But there we are. Which we will be using for some examples as well. But that is in the formula book. But hopefully once you get a bit familiar with this formula as you use it throughout the section. Last thing I need to mention is a sort of special case. And that is actually that we need to define 0 factorial. Because when we have the choose function, so say we have n choose r, but say if we had 3 0 and 4 0 and so on, we need to evaluate this when r is 0, right? Now if we were to do that, remember the formula involving the factorials, that fraction. So n choose r is also n factorial over r factorial with n minus r factorial. Again, you don't need to remember that because it's in the formula book, but here it's and that's going to be n factorial over r factorial of n minus r factorial. Then n is 3, so we get 3 factorial over r, which is 0 factorial, of n minus r, which is 3 minus 0, which would then be 3 factorial again. Now that cancels out, and we're left with 1 over 0 factorial. Now we actually do need to find 0 factorial to be able to evaluate that, and we do need to evaluate that with expansions, because remember 0 here, r is 0, corresponds to the coefficient of x to the 0 of an expansion like x plus a, right? So on, to the power of some number n. So that corresponds to the first term of x is 0. So we do need to find 0 factorial to evaluate the choose function like this. How we go about this? Well, we're actually 0 factorial. Well, actually, we're just going to look at the definition of a factorial, right, that we just looked at. We know that n factorial is n times n minus 1 times dot dot dot, oh, times 2 times 1. What if, well, what if we divide by n to both sides? We then get n factorial over n is now n minus 1 times dot 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 times 2 times 1. But that's just n minus 1 factorial then, isn't it? Right? Because then you times in the first n minus 1 numbers together. And so there we are. Now, what if then I then said n is 1? Right? Then if we got n is 1 into here, this equation, then if n is 1, that means then we have 1 factorial over 1 is 1 minus 1 factorial. Now 1 minus 1 is 0, so that this is now 0 factorial. Well, 1 factorial is just 1, right? 1 times 1, if you will. So 0 factorial then is then 1 over 1. So 0 factorial is indeed 1. So then this goes to 1 over 1, which is 1. That makes sense because then 3 choose 0 again. If you look at our Pascal's triangle, it's there, right? 3, the row 3 here, choose 0. So when the r is 0 here, is 1. So that makes sense, right? So we get 1 there. So the special case is that simply 0 factorial has to be 1 as well. Okay, that will allow you to work out any sort of special choose functions or special factorials, right? Because we all need that, but that's the reason why. Okay, 0 factorial also equals 1, and it does exist as well. But there we are. Oh, and I should also mention, lastly, before we look at examples, this choose function. So again, NCR means N choose R. That's what this C stands for. Now, why is it called choose? Because it relates to the ways we can pick stuff. For example, if we had, say, 7 cards, so 7 boxes of cards, 1, 2, 3, 4, 7, and we call that, say, A, B, C, D, E, F, G. So they're all different, right? They all have different letters. What if I said that, well, there are 7 cards, I want you to pick any 4. How many combinations of cards can we make? How many possibilities are there? So say if I have 7 cards, right? How many ways to pick 4, to pick any 4, right? And so I guess you might think, well, let's just start listing certain possibilities, right? So you could have A, B, C, D, A, B, C, E, A, B, C, F, and so on. But the problem is that can be very lengthy. But that's what this function does as well. It turns out, in the case when we need to pick, when we have n items and we need to pick r from that amount. So say here n is 7, and then r, how many things we want to pick from that? 4, right? And then we can, how many ways of picking 4 different cards from 7? That actually corresponds to n choose r, 7 choose 4. And so we can just do that on the calculator, right? So if we bring that up again, let's have a look at use our calculator again. Okay. So if we want 7 choose 4, where we want 7 and then we want the C. So it's going to be on shift again. Then C, which is there, and then 4 is 35. So this tells us there are 30 ways of, or 35 possibilities of picking 4 cards from 7, right? And so that's why it's called the choose function, because it also relates to giving us the number of possibilities of choosing R things from a total of n, right? But we don't need to know that for now. That's when we look at probability and stats in the applied part of the course. But that's where it comes from. But we're using that again in stats. But yeah, so I thought I'd just explain that because that's essentially the underlying idea behind that. But we can use it just the choose function to give us these coefficients, right? But yeah, let's have a look at some examples of using this then now with this. So example 3. Firstly, it's asking us to calculate 5 factorial. Okay, well, we already did that actually, but to do it again, well, you could remember factorial means every number so every number times to 5. So 5, and then times 4, times 3, times 2, times 1 at the end there. And so that then would be 5 times 4 would be 20, 20 times 3 is 60, 60 times 2 is 120, so that'd be 120, but we can put that in a calculator, again to remind you. So then if we want 5 factorial, so 5, then I want the exclamation mark symbol, so that would be then shift to get it in the yellow mode, and then the factorial button is there, and there we are, we get 120 straight away. Then part B then says 5 choose 2, which is this. So remember the C obviously stands for choose. That's how we read it out, remember. 5 choose 2. So then if we put that in a calculator, again, so we want 5 choose 2. So we want 5. Then the C, which again we put it in shift mode. Then the C is there. And then 2 at the end. And we get 10. Okay. There we are. Cool. Okay. And we can also write that again as 5 2 as well. In this sort of bracket notation. There. Okay. Cool. Then part C then says find the 6th entry in the 10th row of Pascal's triangle. Right now, obviously it says 10th row. That's a lot of rows. So don't use Pascal's triangle. We're going to be using this choose function instead. Now, first of all, the row number tells us n. Now, as I said before, we start from 0. So actually, if we want the 10th row, we actually want n is 9. Okay, we want to knock off row because that's the actual row we want. Because remember, we start from row 0. Because of the fact that we include powers of 0 in our expansion. So we need to knock off 1. So n will be 9. When we have n choose r, right? We want n is 9. Then we want the 6th entry. Now again, we start from 0, right? Remember the 0th entry corresponds to the 0th term of x, which is x to the 0. So the 6th entry would actually be the 5th value of r. So there we are. So basically, we knock off 1, right, to each value, right, from the row and the entry. So then really, this value just corresponds to doing 9 choose 5, right? If we do that then, we get, let's put it back to normal. Well, we want 9, then choose, so shift, and then the C button, for choose is there, then 5, we get 126. Okay, cool. There we are. Yes, and so just to reiterate again, the row, we knock off 1 because, remember again, we include powers of 0, because it's like x to the, this would be x to the 0, add x to the 1, add x squared, as dot dot dot, add x to the 8, add x to the 9. Now those are 10 terms overall because we're counting from 0 to 9, right? Not from 1 to 9. So those are 10, so that's the 10th row, but actually it's we only want 9, right? Because the power is 9, right? We have 10 terms, but the power is 9. The power is the key idea here. And then the 6th entry, again, this is sort of the 0th entry because it's x to the 0. And so the sixth one would actually be 5, right? Which is where we get 5 from there. So there we are then. So it's a bit weird to get your head around the fact we actually have to knock off 1 because of the fact we're counting from 0. It is a bit weird, I know, but that's sort of how we operate, because the key idea is in our expansion we do include 0th powers, okay? Okay, so we have some exercises then. So, we're told in this question the 14th row of Pascal's triangle is shown below. 1, 13, 78, and dot 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 dot. First of all, it wants us to find the next 2 values in this row. So remember, it's a row of values on Pascal's triangle. Now, what we shouldn't do is just list the first 14 rows of the triangle, right? Because we can very quickly find it using our choose function. Now again, it's the 14th row, so remember, because we're starting from 0, it's actually going to be n is 13, right? That's the whole idea. The row number where we knock 1 off when we're using n choose r. Then r, so our position, right, is going to be what? Well, well, first of all, for this next term, well, that's r is 0, r is 1, r is 2. So this one's going to be r is 3. If we were to look that out then, 13 choose 3. If we put that in a calculator, that's going to get us, again, use our calculator. 13, then choose shift, then the C button here, choose 3, gets us 286. Okay, but then we want the next row after the next value after that. Well, again, it's n is 13 because it's sort of the 13th row, but n is 13. But then we want the well, it'll be r is 4. We want the 4th position, right? Because then that'd be 0. R is 1 here. R is 2. We found r is 3 there, so r is 4 will be next. So 13 choose 4 then will give us the next value. So then that would be 13 choose 4 is 715. And there we are. Cool. So that's just hopefully start to recognise how we can translate and switch between Pascal's triangle and this sort of n choose r notation, where we can quickly extract the numbers from Pascal's triangle, right? And the idea is just we basically start from 0, right? And count from there. Anyway, part B then, that says hence find the coefficient of x to the 4 in the expansion of 1 plus 3x to the 13th. So we want the x to the 4 term here. So again, x to the 4 term. How are we going to do that then? Well, remember, we're going to have x to the 4, right? That we're going to have an x to the 4 term. Well, it won't be x to the 4, will it? Because we have 3x, right? So it would be 3x lots to the 4, right? Then we have plus 1, so then 1 will be after. Now, it has to add up to 13 the powers, so it's going to be 1 to the 9. There. But then we need a coefficient part as well, because remember, every term is going to have a coefficient part, then an x part, and then the other number, right, in the bracket. Well, then we need the coefficient part. Well, that's going to stem from n choose r. So we have the overall n is 13, right? That's the power. But we want x to the 4, so the power here is 4. And so that is our overall x to the 4 term. Now we can just deal with all the brackets then. So firstly, 13 choose 4. Well, again, we're going to use our calculator for that. So again, just to show you, we want to find 13 choose 4 in the calculator. Oh, actually, we worked it out. It's 715, right? So that'd be 715. Because that's from part A. Yes, because 13 choose 4. 13 choose 4 was here. So there we are. Anyway, we get 715, and then we need to expand 3x all to the power of 4. Again, it's 3x, not x, because that's what we have here. Remember, when we do expanding in this way, we include the first term in the bracket, and then the other term as well, which would then be 1. Anyway, 3x all to the power of 4. That's going to be, well, 3 to the 4 is 81, I believe. 81. So then it's going to be 81 to the power of 4. Then we have 1 to the 9. Well, that's just 1. So overall then, 715 times 81 is 57915 x to the 4. So there we are then. Okay, so we've got the simplified coefficient for x to the 4. Well, it told us, well, there we are then, that's the coefficient, right? Therefore, coefficient of x to the 4 is 57915. Cool. And so generally, that's the idea of how we use binomial coefficients, and we'll be using lots more in the next few sections as well, next few videos of this in practice, where we expand many different brackets. But that's the overall idea. The choose function gives us the coefficient part of an expansion. So for any particular term, we then calculate the n choose r, right? Then we have the x part, and then the other part in the bracket, right? So there we are. Okay. Okay. And the last two questions, we're going to look at stuff to do with this definition again. Remember, n choose r can also be explicitly written down as n factorial r factorial n minus r factorial. Now again, that will be in the formula book, but let's try and get some. But you need to know how to use it, right? And that's what these questions are going to look at. So firstly, we're given 35 choose p is 35 factorial over p factorial 18 factorial. And so if we use this formula and literally compare it, well, 35p, right? If we were to use this formula, well, n is 35, so that'd be 35 factorial. Then r factorial would be p factorial. Then n minus r, well, that's going to be 35 minus p factorial. If we compare these two fractions, well, here we've got 18 factorial, right? And here we've got this. Everything else is the same, so these must be equal. So 18 factorial must be 35 minus p factorial. Well, the factorials kind of cancel out. So therefore 18 is just 35 minus p. If we then solve for p, well, therefore p is going to be 35 take away 18, which is then going to be 17, I believe. Yes. So therefore p is 17, okay? So that is, again, how we can use the formula to solve certain problems like this, by just comparing certain terms in this way. Okay, there we are. Last question then, I believe. Some more stuff to do with factorial. Again, I'll reiterate the formula. So n choose r is n factorial over r factorial of n minus r factorial. And so we are told to show that firstly, n choose 1 is n. Now remember, we can also say n choose 1 is n in terms of this bracket, alright? Both of these notations are the same, but there we are. Okay, now, obviously we can't use the calculator because the calculator does not work with unknown values. We'd need to find a value of n. So we need to resort to this formula. Now, n choose 1, where we can kind of we can use this formula then, because we know r is 1. So if r is 1, then n choose 1 is going to be n factorial over r factorial, which is 1 factorial, of n minus r, that's going to be n minus 1 factorial. Now 1 factorial it's just 1, right? It's just 1 times 1, if you will, right? So that will simply just go to n factorial over n minus 1 factorial, and there we are. Now, at this point, a common strategy here with these sort of questions is you need to consider the factorial definition. So n factorial is actually just n times n minus 1 times dot 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 times 2 times 1, right? It's the first n numbers times together. Likewise, n minus 1 factorial is going to be n minus 1 times by the other numbers times 2 times 1, right? It's the first n minus 1 numbers times together. Now, hopefully at this point you recognise, well, n minus 1 will cancel with n minus 1 here, and then all the terms there will cancel, and 2 will cancel here, 1 will cancel here, because they're all common factors on the top and the bottom. It's like cancelling factors with algebraic fractions, right? So all those cancel, and simply we get left with n. Well, there we are then. We've shown that for any value of n choose 1 is indeed n. Okay. Now for part B, we need to show that n choose 2 is n of n minus 1 all over 2. Again, we can alternatively write this as n2 is this. Okay. So again, if I were to bring my formula in, n choose 2, we have n factorial. Then r is 2, so we're going to have 2 factorial. Then n minus r is just n minus 2, all factorial. Now again, my 2 factorial we can work out. That's just going to be 2 times 1, which is 2. So we get n factorial over 2 times n minus 2 factorial. Now again, the idea is, again, we can use the definition of a factorial, sort of kind of expand in a way, to then get, well, n factorial was n times n minus 1 times n minus 2 times dot 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 times 2 times 1. And we can do the same to n minus 2 factorial on the bottom, because then we have 2 times, well, n minus 2 factorial is n minus 2, and then dot dot dot, we go down to then left with 2 times 1 at the end there. So it's the first n minus 2 numbers times together. Now again, we can start to cancel common factors out. Well, n minus 2 here and here cancel, and everything afterwards will cancel out. 2, 2 and 1 will cancel. So we're left with simply n times n minus 1 over 2. Right, we just got this 2 here. And so actually we can just bring that together to get n of n minus 1 over 2. Well, what do you know? There we are then. There we are. We've shown it. So yeah, they don't ask this. I don't think I've ever seen a question in the A level ask a question like that. You never know. But they're not too bad. But hopefully you understand the idea, right? But we use this definition to prove certain stuff about the choose function like this. We can use this definition, and then we can sort of use the factorial definition, right? The factorial being we times the first n numbers together, and we can cancel stuff out, and so we can simplify it that way. But yeah, so that is what we call the choose function and factorial notation. Hopefully you start to get an idea of how to use it. We will be using it more in the next section when we look at expanding certain binomials, using this idea. Be using it more and more, so you get more confident with it. But that's just a brief sort of overview and introduction to the choose function and factorials. So I'll see you next time.